Welcome back. So now we will continue our discussion on this wind energy. But here, mostly what we are pretty much we have done our what I would say the major theoretical component of the discussion. So now if you recall from our last few sessions that we are talking about the design purpose and all these things. So for design, what we have discussed is primarily the linearized model or the simplified model, like that. And those simplified models and all these things, those are very, very useful for initial design purposes. And once we get the initial design data, then we can move for more detailed analysis like that. But as I have kind of emphasized that the wind turbine design procedure is a complete aeroelastic problem. Or so what we are trying here is all analytical ways or simplified method which could provide us the initial data. And using that data, we could come up with the initial design parameters. So which could be rotor hub, rotor diameter, then the blade, airfall, and all these things. So while doing so, one of the important factor that has to be considered is that all these simplified model that we have, these are these models have some limitations. Um, some models can take care of certain phenomena, some models cannot take care of certain phenomena. And that's what happened while discussing about those particular conditions when we are talking about what you call the talking about that the rotation, hinge spring models, and things like that. Now, having said that, coming back to the primary thing is that, okay, what you can do, you can have those simplified model and things like that. So those simplified model, which are good, which are useful, which are handy for getting initial design data and all this. But that still doesn't give you the complete picture of that. So, and also we have talked about how one can obtain different structural behavior of the whole unit. Whether you talk about tower, whether you talk about the rotor blade, whether you talk about the nacelle, mm, or in combination with the complete unit. So structural response also, either you can do simplified analysis, you can do modal analysis, you can do lump parameter analysis, you can do multi-body dynamics, which are quite involved, or you can do complete finite. Similarly, while you are talking about the load calculation on these different components, that's the aerodynamic load primarily, because we are trying to extract out the wind energy to produce electricity. Uh, so aerodynamic calculations also we have discussed quite enough about this simplified aerodynamic model, how to estimate those forces and moments and things like that. Now, alternatively, one can completely do CFD. Now, today's date, the computing power has evolved or matured enormously. So you have huge computing resources. Now, so your CFD methods or the methodologies, those are also quite matured at this stage. So CFD can be used to um, completely analyze those three-dimensional load calculations. So in that context, we are going to talk about the, the basic CFD perspective, that what CFD does, then how we can apply to those in the wind turbine or this kind of rotating frame of reference applications. And then uh, finally, we'll conclude with some alternative concepts and things like that. Okay. So that is why we are going to talk about on CFD perspective of this wind turbine. So here, if you see, you, I mean, we can start with the role of CFD in a role of CFD in engineering applications. You can see this is an application which is flapping of bird. Then we have next one, flow over this morphing wing, noise. These are AI ML application. This is wind turbine application. This is it. So this is electrochemical system, gas turbine application. So there are different applications. So you can see CFD has been applied in different areas at this moment. I mean, these are only to name a few. It's not that the list is completely, I mean, but this should give you an idea that now CFD has been used in different engineering applications. So when you talk about CFD, it tells you some or raises some questions. So now when you talk about the academia or academic people, can academia play a role in supporting the industry? When you talk about design and all these things, these are important in industrial application. So can we support that? So can the academia play a role in supporting the industry? So this is where it's very, very important that when you have this, that how is because academic people can come up with the new technology development and things like that, and how they help the industrial design procedure. Can the company or the industrial people take advantage from scientific expertise? Because academic science or academic community has the scientific expertise which can be used by them, and also academia learn from the people employed in the company because they are experienced in day-to-day operation, they are experienced in handling a practical problem. So it's an win-win strategy of cooperation. So if the academia handshake with the industry, then it's probably the best possible situation to design something in scientific world, where one hand the academia can provide the technological know-how, and that can be taken by the industry people for further development and taking to the actually the design procedure and finally do that. So now, what are the possible answer? That obviously the academia can offer competence perceived as an advantage. Okay, so this can be utilized. Then interdisciplinary approach to solve the issue. That means so interdisciplinary approach to solve the issues. Then capability to redesign with a focus on product innovation, and capability to predict the change of demand from society. So it's essentially an innovation that we are talking about. That this one-to-one handshaking would help to kind of go with that. Now, what is computer aided design? That it's what it does. it's kind of an use the computer software to doing the engineering analysis. So initially the picture that we have seen primarily that shows that how the computer aided tool, which is a common in the all the industry which are in design and manufacturing process, they are involved. So it can so the tools which involve finite element analysis, which we talk about when you talk about the structural responses, when you talk about then multi-dynamics, which is also a tool that is also we talked about because the multi-body dynamics is important for designing certain component of this optimization procedure. There could be some more. These are only few listed here, and CFD. CFD is used for the fluid flow problems, fluid flow and heat transfer problem. But when you go to structural or solid mechanics problem, you need finite element analysis, you need multi-body dynamic, and all these things. So, uh, any software that has been developed to support these kind of activities are termed or considered as the CA tool. So the CA tools are used to analyze the system. So it encompasses simulation, validation, optimizations. So what is the future? The CA system will be the major provider for information to help support design team. So this is why we are talking about this CFD perspective. And but this is also true for even talking about the structural dynamics or multi-body dynamic system that we talk about it. But yes, when we talk about the CFD, then it's for fluid flow and heat transfer related problem. So what is CFD? As I have been saying this. hmm, this it's a tool which deals with the fluid dynamics and heat transfer problem. So this is what I was talking about. But the CA tool could be also finite. Is CFD is an alternative to measurement because if you talk about wind turbine, it's such a large system after design and all these things. So doing measurements, a tunnel and all these things, that could be a challenge. This is where the CFD could be handy to. So this has an application in multiple areas, and I'll show you some of the example. So these are becoming a key component for computer. Now, so how the CFD works? I mean, if you try to see that, so when you have a fluid flow problem, then essentially the tool is going to give you solution to a physical problem. So you have that physical problem. So essentially, which is the problem of fluid mechanics or heat transfer. So you understand that, and then you try to find out the governing equation. So typically in fluid flow problem, things are defined by the Navier-Stokes equation. So first thing is that you try to, it's a mathematical tool. So you have a physical problem, let's say flow over aircraft wing, flow over wind turbine. So what mathematical equations or conservation equation, anything in nature, they are governed by this basic conservation equation. So we try to find out what is the conservation equation that govern that particular system. So we identified that particular, those governing equations, and those are the partial differential equations. Then we apply different numerical methods. Even CFD, there are multiple ways one can do. One can use. We'll talk about that as we go along with this discussion. Uh, we try to apply those numerical methods, then get a mathematical form, which is a linear system. Then that combined with the geometry, that actual problem, for example, flow around the turbine, which we call is a grid. And then we convert that to computer program. And then program finally get us the simulation results. Once we analyze, that's how the get the. So this is what the complete cycle of the CLP, that how whole these processes are done. So that means it closes the complete loop. So there are primarily three different stages. Okay, three different stages. One is the pre-processing stage. That is the stage where you try to define the geometrical model, the physical model, and the boundary conditions. Then you have computing where you do that, and then the post-processing. So if you look at it, then you have this pre-processing stage where you define the physical model and then have this grid ready. Then you do the solution in the using your numerical tool during computation, then finally analyze the. So this is an iterative process. That means once we get our results and the results are not good, you go back and make some corrections, and then again you redo this process. So this is how it happened. You first identify the geometry or the physical problem, then the geometry you set it up. Once you set it up and everything, then you send it for the simulation. Once you simulations, you get the results to analyze it. So this is how the whole process actually works. So what CFD is, it's a science of predicting fluid flow behavior by solving the governing equations in a numerical framework. So this is what it does. Okay. Now, so by solving this and the result of CFD analysis, so that represent valid engineering data that may be used for conceptual studies of new design, studies where control experiments are difficult to perform, for example, wind turbine case, studies with hazardous operating conditions, redesigning the system, then analysis represent a valid competent to experiments and all these things. So what is this? This is essentially analysis and design. Okay. So you have a simulation based design instead of build and test. So this is cost effective. Okay. Solution provide high fidelity database. I mean, obviously the any full scale simulations can be done. It is not hazardous. Physics can be completely. So what is important here is that if you compare side by side, again, while we're talking about any CAE tool, whether it's a finite element or CFD for fluid flow problem, please understand one thing, that this is not going to replace your measurement or experiment techniques completely, but this would reduce your design time and getting a data where your measurement cannot be done. Okay, so simulation can be cheap because it's only computer based simulation. The time is short. There is no limitation to the scale. You can do complete scale simulation. um, the complete information is available. It's repeatable. There is a it is not hazardous. These are the advantage, and that is why this should go hand to hand with the experiments and should be used as a preliminary design data, which can be obtained from the CFD or any CAE tool in that way, and that can be taken for the further decision making process. Okay, so again, coming back to the CFD thing, so what so what you can, so it's a computers which are built in 1950. There we could do limited floating point operation, but today we can do exaflop floating point operation. So the whole idea is that the computing infrastructure has really gone that much that we can do today's that kind of computing, which was not possible. So obviously this was possible because of high performance computing platform. So high performance computing platform uses a kind of an aggregated computer system, or we call it a supercomputer. So there are multiple cores of the processors are available. So your performance can go up and you can get simulation done in a quick turnaround time. So why do you need those HPC? Because your lab computer cannot do those things. You want to increase your complexity with existing calculation, which your lab computer laptop cannot do. You need to specialize resources which are not available in your lab computer. So this is why the HPC environment comes into the picture. And you can see this is a supercomputer with high level computational capacity compared to general purpose computer. So that means you have those which are, this was first compute HPC was introduced in 1960, which is a Cray system, which massively parallel computation can be done. So that means what you do, that you kind of distribute your task. Instead of it just, you can think about, I have one laptop or one desktop. Here it's a multiple desktop which are connected to each other. So the task what your desktop and laptop can do, now you are distributing that whole task in multiple laptop and desktop to do that, and that is through this parallel processing and all these things. So you can solve those great challenges. You can solve those large scale problems. You can solve the huge problem. And as I said, that we can do, I mean, now Gitaflop calculations, not even exaflop, Gitaflop calculations. Today we can do that. That means the supercomputers are so powerful that you can do this much of calculation. But while doing that, the key ingredient here is the parallelization. So that means your software, the CA tool, that has to be that must be able to execute over these multiple laptops or desktops or multiple this HPC environment. So the CFD or CE tool development is another challenging area where scientists and engineers are working. They are developing every day different tools. That's what I started. That today the CE tools are quite matured. They're quite powerful. They're hugely scalable over this computer, so that you need to do this tasking over multiple computers rather than doing it over a single computer or single laptop or single desktop. So that's what you can solve this problem. This is an idea about how this was a list from November 2023. I think every 6 months they release this data, so one can go this particular site and get this data out. That this is a country wise here. Obviously, United States dominates most of the supercomputer, and this is performance here also. Here, the United States kind of dominating, and it is a spectrum of application. If you see, it is quite mesmerizing. Okay, so it has been. I mean, it is everywhere. Okay, kind of. So that's what one has to see, that this is everywhere. Uh, so these are some of the top computer based on their performance, but you can go to that top 500 site and get this data. It is not something hidden or not available of such thing. So these are readily available, and this is how performance development. So this is what is projected, how the floating point calculations would go. And this is the projected performance. So that means the computers are going to be quite powerful. So that means the performance improves by factor of 10 every 4 years. So this is where, that means you can think about the kind of calculations that you can do today. Maybe 4 years down the line, you could be able to do 10 times higher, I mean, complicated problem or that kind of problem of that nature. So this is where the computing platform and all these things. This is where, as per 2023, November 2023, from this side, the Indian supercomputer list. So this is in the CDAC. This is also CDAC. This is Indian Institute of Meteorology. And so obviously this year list could have been a different list. So now if you see the application is everywhere. Okay. So whether you talk about aerospace application, whether you talk about appliances, automotive industry, so that means pretty much every industry. That's what I started with, that nice picture of showing different kind of example, that where are these role of CFD or CE tool in different areas. Its complete spectrum is quite huge. Okay, so different IDs, different, I mean, sector, they are heavily used. So that's how your application of CFD is. Now the CFD solvers, There are commercial solvers which are available. There are in-house capability. There are academic solvers. There are open source codes. I mean, these days there are plentiful open source codes which are available that one can use and do that. How this problem is solved, we have talked about it. So the physical problem that you want to solve from the continuum real problem, simplified mathematical problem. So this is your pre-processing, then you model setting, then finally you solve this problem. So it's a tool that requires you to switch your brain and your fantasy. Essentially, what it does, you identify the problem, their governed equations, convert to a mathematical problem, do the programming, set up instruction to the computer to solve it, whether it's a single computer or over this HPC environment, get the simulation result done and then analyze it for and use it for design purposes. That's how it works. So just to problem identification, that is pre-processing stage where you identify the problem. Let's say this problem, this is how you generate the grid, setting up where your partial differential equations, then your computer program which are going to run over this HPC. Finally, the result once you analysis done. So you have cost, time, ability to simulate. These are quite advantageous. Obviously, physical models, numerical error, boundary conditions. So one has to be very, very careful while doing this. Then they should not commit to such mistake, which could lead to a problem of that. Okay. Now, so when you talk about fluids are having liquid and gas. Their density could be constant for incompressible and variable for that. Then viscosity is there. So these are some of the physical, or these are the transport properties or properties of fluid. Okay. What happened in the fluid mechanics? You have inviscid flow, you have viscous flow, which could be laminar and turbulent. Then again, laminar can go to internal flow like pipe, valve, external flow, airfoil. So our wind energy, wind turbine belongs to the external flow. So this is where our wind turbine belong to that turbulent external flow. Then you have compressible, incompressible, but most of the time we are dealing with incompressible situation here. So TFD codes typically designed for, I mean, it could be, I mean, that is why the problem definition is very, very important, that what we are going to use now. There could be viscous or inviscid situation. There could be laminar or turbulent situation, incompressible versus compressible, single versus multi-species. So these are all these numbers which are there. These are called non-dimensional number, which are non-dimensional numbers which are used. So obviously, one can have a quite generic CFD code, but also which can use for multiple purposes. But there could be some specific purpose codes which are also available, because every problem, the nature of the problem is different. So dealing of those problems are also slightly different. That's what happens. Now, when you talk about Navier-Stokes, these are the two great scientists who came up with this Navier-Stokes equation. So here you have this conservation laws. So first basic conservation law is the mass conservation. Then you have mass, momentum, and energy. Obviously, when you talk about the wind turbine, then you have also angular momentum conservation that is required. And when you deal with the reacting system, then you have a species conservation and all these things. So continuity equation talks about the mass conservation equation. So this is a complete continuity equation one can use, but this is the simplification for incompressible. So for incompressible flow, for example, for wind turbine, mostly we will be dealing with incompressible situation. So here this simplified in continuity equation would be good enough to use. Then you have momentum conservation equation. So this is a local time derivative term. This is convective term. This is pressure gradient term. This is or surface force. This is diffusion term, mass force term. So these are, now you can again simplify for incompressible flow, and this could be used for incompressible situation, this kind of equation. Okay, so now if you look at the energy equation, this is written in terms of temperature, but the energy equations can be written in multiple form. So there are different forms of energy equation. Could be written in terms of enthalpy, could be written in internal energy, could be written in terms of total energy. So there are different form, and this is written in terms of temperature, where again you have time derivative term, convection term, pressure term, heat flux term, and mechanical energy term. So these are the different term which are associated with this. So when you talk about wind turbine, so you need one more additional conservation equation, which is angular momentum. That because this is a rotating frame of system, so anything rotating, so it is not only wind turbine, whether hydro turbine, whether pump, compressor, so you need angular momentum conservation also. So, and if you recall towards the beginning of that, we are talking about the wind turbine VX, and where the angular momentum is getting conserved. So this is something is also required. So that means you need basic conservation equation to solve this. Continuity or mass conservation, momentum conservation, energy conservation, and angular momentum conservation. Now we'll stop the discussion here and continue the further discussion in next session and conclude it. Thank you.